Welcome to my second video lecture on Laplace transform. I've shown you on a Zoom meeting as well as the previous video on the concept of Laplace transform and what it is and what it does. In order for us to start working with Laplace transform, we must first look at fundamental definitions and some properties of what Laplace transforms are, and then we'll get into the mechanics of it all. Now, in general, when we have a function, f of t, we could take the Laplace transform of it just like that, and that's the notation. So Laplace transform of f of t, by definition, is some infinite integral, 0 to infinity, or improper integral, of the function f of t times its kernel, which is e to the minus st dt. And by definition, that's we call f of s. So when you take the Laplace transform of a function in time domain, you get a function in frequency domain. And that has an interesting property that it turns differential equations into algebraic equations, which is the cornerstone of why we're doing this. Okay, so there's the fundamental definition of Laplace transform. Now, in order for us to work with Laplace transform, we have to determine if it's a linear operator and the difference between an operator and a transform. Let's start talking about what's the difference between a transform and an operator. Well, I have a couple of pictures here that I'll hope will give you the picture. Now, if you have a transform and a function goes into it, what comes out of it is a completely different function, but besides that, it's also based on a completely different variable. So based on a completely different domain. So a transform, it doesn't just transforms the function, it also changes the domain of the function. So when you put in a t variable into a Laplace transform, what comes out is not only a different function, but it's also a function based on frequency variable. And thank God it's a linear transform, and you'll see when I actually prove it for you guys. But an operator, like a differentiation process, or an integration process, or a summation process, or a limit process, these are all called operators. Why? Because if you apply any of these to a function, of course, the result is going to be a different function, but notice it's going to be based on the same variable. If I take the derivative of f of t, then the result is some other function for sure, obviously, but it's still going to be a function of t. But if I find a Laplace transform of f of t, the result is going to be some other function for sure again, but it's not going to be based on t, it's going to be based on s, and that's the magic, and that's what makes the differential equation turn into an algebraic equation. That's just gift of nature to mankind, and Laplace noticed it. Now, talking about the linearity of Laplace transform, I'll do this very quickly. Laplace transform is a linear operator, which means it's closed under addition and scalar multiplication. And basically what that means, because a lot of people say, what do you mean by closed under addition? That means when addition goes in, it closes the door and locks it. Nothing like that, just a language. Closed under addition and scalar multiplication basically tells me that if I take the Laplace transform of the sum of two functions, that would basically be the Laplace transform of each individual function. You can derive Laplace transform through addition is basically what it means. And also if you have a constant multiple, you could always pull it out. But I'm going to do the proof for the summation. So I'm going to prove that Laplace transform of f plus g is indeed Laplace transform of f plus Laplace transform of g. And in order to do that, just like you did the fundamental proofs of derivatives when you had learned it first, we always use the definition of a Laplace transform. So the Laplace transform of f plus g would be the integral from 0 to infinity of f of t plus g of t, which is now my main function, my h of t, e to the minus st, which is my kernel, dt. Now, I do know that integration is a linear operator for sure because I've already proven it. So I could write this as 0 to infinity of f of t, e to the minus st, dt, and I could separate it, plus the integral from 0 to infinity of g of t, e to the minus st, dt. And if you notice, oh my God, this is the very definition of Laplace transform of f of t. And oh my God, again, this is the very definition of transform of g of t, Laplace transform of g of t. So you notice that Laplace transform of f plus g is indeed Laplace transform of f plus Laplace transform of g, which you could write it as f of s plus g of s. Two new functions and two new variables in terms of s, known as the frequency domain. So that's how you prove that Laplace transform is a linear operator. Now, in order for us to work with Laplace transform and use it to solve differential equations, which is our ultimate objective in this chapter, or in this module, we first need to learn how to find Laplace transform of some basic functions using the definition, which pretty much boils down to you guys doing a whole bunch of integration by parts, or any kind of an integration technique that you've learned in second semester calculus. So, but before that, let me just talk about some more definitions of Laplace transform and some properties. Now, these are theoretical, and the proof of all of these is for a more advanced differential equation class. But at this point, I just want to mention it to you. I already talked about the definition of Laplace transform, which is the integral of the function that you're trying to transform multiplied by the kernel of transformation, which is an exponential here. That's what makes the magic happen. And this is said to be Laplace, so f of, and that's, by the way, equals to f of s. And that's said to be the Laplace transform of f, provided the integral converges. Now, we're not going to focus a lot on convergence issues in this chapter for the Laplace transform, but suffice to say that there are some restrictions on functions in which you can find a Laplace transform of, and the restriction is known to be called an exponential order. Basically, you notice you're finding the integral of a function multiplied by an exponential, a negative exponential. Now, why is a negative exponential used here? If you think about the convergence of it, a negative exponential is used because if you notice, and if you recall, a negative exponential is a fast decaying function. It's a very fast decaying function. And if you want your integral, your improper integral to converge, if you're taking an integral of some function f of t, you want to make sure you have enough of a sort of a solvent here that would be able to actually push the function, even though f of t could be quite erratic. But you have a very, very fast decaying function that's multiplying it so that either the negative st will force that f of t to behave so that the integral could converge. That's the best way I could say it. So it's basically the protector, or the person that keeps f of t in check. So therefore we say f must be of exponential order, which means basically that if you use a function that grows much more erratic and faster than either the negative st decays, then that integral won't converge because either the minus st won't be strong enough to control f of t, and the integral will go out of control and obviously won't converge. So therefore, we can only use functions that are of exponential order, which basically means this definition that the ultimate see, they write this, that means the biggest f of t could be has to be less than some multiple of an exponential. So that, because if that's the case, then the exponential function that we have in the transform will always overcome f of t and its chaotic behavior or its non-converging properties, and it will make it behave so that the integral could converge. So we can only use functions of exponential order here. And I've given you a picture of some of these. So you see the f of x always has to be below the exponential, so the exponential is stronger so we can kill it. And you see three function of exponential order. See, here's a function. It's below. It's below the exponential, so the exponential overcomes it. So this is an okay function to use. The Laplace transform of this function will definitely converge. E to the minus t. Again, you see it's being overpowered by e to the t. E to the t is stronger, so that's okay. Cosine of t is okay because again it's weaker than e to the t. It's bigger than that, so e to the t, if it's negative, will suppress it. So these are all known as exponential order functions. And we have to be careful when we're doing research and development or we're working on some theories that the functions you work with are of exponential order before you spend any more time dealing with them. But in this course and in this lecture, the functions we're working with are going to be assuming that are of exponential order, so we could focus our attention to basically do the mathematics and not worry about the R&D aspect of it. So we'll start with, as I said, taking the Laplace transform of a few fundamental functions. We call it elementary Laplace transforms. So for example, you want to be able to know what the Laplace transform of 1 is. You want to know what the Laplace transform of a t is. You want to know what the Laplace transform of t squared, t cubed. You want to know what the Laplace transform of basic exponential is. You want to know what the Laplace transform of a basic sinusoid is. And you want to know what the Laplace transform of a basic cosine function is. And we can also do Laplace transform of the sinh function and the Laplace transform of the cosh function. See, these are I call these like the very fundamental, the ABCD of Laplace transform. So in order for us to get into Laplace transform, we initially work on finding Laplace transform of some of these fundamental functions using the definition. And that's what we're going to be doing next. So in the next video, I'll be showing you guys how we can go through and actually find the Laplace transform of some fundamental functions for us to get our feet wet with finding Laplace transforms. Thank you, and see you guys on the next lecture.